All right, let's get started. So first off, you have a homework assignment due on Monday. Let me pull something up real quick. I'll admit, with getting ready for the technical conference yesterday, I had meant to send an email out to the class, and it sort of slipped my mind. So since everybody's here, I'll go ahead and show everybody. So on problem 2 is asking for a lot of factored responses, like factored moment, factored shear, factored load. You can treat 50 PSF as the factored load. Assume that that's already gone through live load reduction and already gone through 1.2 times the dead plus 1.6 times the live. So you can just take that 50 pounds per square foot and distribute it accordingly. The purpose of this problem is really more on your ability to handle a floor system that's not a nice, neat, even grid. The last problem was more about, okay, nice, neat, even grid. Let's do some live load reduction. Let's do some load factoring. Let me get this passed around. I did forget the sign-in sheet in steel design, but earlier I forgot one in concrete design, so I think it all kind of matches or evens up or something. I don't know. All right, is everybody okay with this? Okay. Your homework is due on Monday, so let me ask, does anybody have any questions about it? Everybody good? Have you looked at it? Seriously, anybody got any questions? Okay, all right. For part B?
Yeah, where it's like coming in like this together, would it be the same way? Would you go like halfway over from the...
Yeah, so if you're looking at this column and you're trying to determine the tributary area, it's literally halfway up here, halfway over here, halfway down here. So you're going to have like an L-shaped little area in the middle.
I mean that girder for B2, B3.
B2, B3, this one right here. Okay, all right, so here's what I'll say about the girder. So we're talking about determining the response on this element right here, right? Okay, all right. What I'll say about that is this, okay? So remember, when you've got girders, you're not going to be taking a pressure load and turning it into a uniformly distributed load. You're going to take, remember, the hip bone connected to the leg bone, those reactions distributed over, right? Okay, now, remember what we did on our example problem. Like we got the reaction on each floor beam, but then we said, we'll take that and multiply it times 2, and that'll be the point load. You remember that? Is that going to be the case here? No. And why?
Because you only have beams framing in on one side.
Yeah, there's only a beam framing in, right here. So if for this floor beam, okay, I'm just making up values. Let's say the reaction over here is 4 kips and the reaction over here is 4 kips. Then when you do this girder, it's literally just going to be 4 kips. 4 kips. 4 kips, something like that. All right? If there were floor beam framing in over here, then it'd be 8 kips, assuming all the dimensions matched. Sound good? Everybody okay? All right. Okay. All right, so just a couple other things. Technical conference, if you're interested in attending, make sure that you are, I don't have it on the slide, but you all should have gotten an email, sometime this morning regarding registration. If you're going to hop in for a session, just pop in and watch one presentation and leave, I don't think it's really that necessary that you register. But if you're going to be there a while and you're planning on networking and rubbing elbows with some potential employers, you need to register so that we'll have a name badge for you. Because if you don't do that, then we don't know you're coming, okay? So you all should have the link. It's pretty basic, pretty straightforward. Everybody okay with that? Okay. The Society of Professional Engineers Scholarship is due today. So I'm sure you can find that on Google if you haven't been able to find the email. So if you're interested, you need to go ahead and knock that out as soon as you can. Everybody good? Okay. So today what we're going to do is we're going to continue on with this discussion of cracking moments. All right. So let's see. Okay. So let me go to this. There we go. No. I thought I had it. Shift F5. There we go. So last time what we had done was we had started to address the principles of beam behavior as the load continues to increase. So the idea is we have a typical reinforced concrete beam and we start applying load. Now under fairly low levels of load, a concrete beam is really going to behave like any other. It's just going to have respond according to sigma equals my over I, one of the more fundamental expressions that you learn in mechanics. So one of the first steps that we like to do in reinforced concrete design is start to ask ourselves, when does that philosophy become invalid? In other words, if concrete is a material that behaves poorly in tension, at what point do the regions in tension begin to experience cracking? Okay. Now, in order to determine the cracking moment, it's a pretty straightforward calculation. You just take your modulus of rupture, your gross moment of inertia, multiply those two and divide them by your extreme fiber distance, which, again, there's no magic behind that equation. It's just sigma equals my over I and just solving for the moment. So that's all there is to it. Now, if you've got a problem like this, which is just a rectangular beam, then the moment of inertia and the extreme fiber distance are really simple because the I is just BH cubed over 12 and your centroid is just halfway up. That's it. It's simple. When you've got a problem like this, the moment of inertia and the centroid are not as easy to find. Now, if you had me for deformables, we do moments of inertia in a little bit more, of a systematic fashion. You probably remember us drawing out a big table and doing the AY over A and doing the parallel axis theorem and whatnot. If it's been a while since you've done that or you're a little fuzzy, no big deal. This problem will serve as a really nice refresher. So this problem is very very similar to the one that we did previously. The only thing that makes it complicated is the moment of inertia. In other words, once we get the moment of inertia and the centroidal distance, it's the same equations. It's the same sigma equals my over I. All right. Sound good? Okay, so we'll take our time with this. So we're looking at example 3A, and then 3B is going to be a little more intricate, but we're taking the same beam, and instead of directly just computing the cracking moment and then ending it, we're going to ask ourselves, if the beam's 24 foot long, how much load can it carry before it cracks? So this might give you a little bit more of an understanding as to what's going on. All right, sound good? Okay. So example 3. We got a 3A and a 3B, but it's all going to be very much the same problem. Okay, so the first thing that we need to determine is the moment of inertia of this cross-section. Now, let's do the moment of inertia. So this is really going to be verbatim out of Engineering 216. Okay. We good?
I was saying I have this exact problem on my head.
Oh. There you go. You might have gotten it right. So, all right. Okay. Let's start off by drawing out our cross section. So our cross section looks something like this. All right. Now, let's start putting in some dimensions. So this is 12 inches. What do we have here? What is this? 27. This dimension right here is what? 5. And this dimension is 60. There we go. Okay, now, before we start doing moments of inertia and centroid calculations and whatnot, we need to do two things. Okay, the first thing that we need to do is we need to break this up into simple shapes. Okay, in other words, a bunch of simple rectangles and what have you. So what I'm going to do is I'm going to say, all right, let's just do this. And let's say that this is rectangle number 1, and this is rectangle number 2. It doesn't matter what numbers we call them. We just need to break it up. We could break it up any way we want. We could actually, if we wanted, we could have broke it, something like that, something like that, and then dealt with 3 rectangles. It still would have worked. I think that would have just been, in fact, a little more grunt work. Okay. Sound good? Okay. That's the first thing we need to do. The second thing we need to do is we need to define what I call a common datum. Okay. Remember when you compute a centroid, y'all remember like sum of AY over sum of A? Those Y distances all have to be referenced from a common point. Okay. So typically what I do in a lot of these problems is I say that the datum starts at the very bottom. So that's my datum. Okay. Sound good? All right. Like I said, this is just going to be straight verbatim out of Engineering 216. So if it's been a while, or if you're feeling familiar with it, this might be a little boring, but if not, it'll be a nice little refresher. All right. Below here, I'm going to draw a big table. So, so be wary of that. There's going to be a lot of columns. So it's going to be a table that looks something like this. All right. Okay. Now this first column over here, I'm going to list shapes. Okay. Now this cross-section has shape 1 and shape 2. All right? And then on the bottom, I'm going to sum stuff up. So sums are down here. Okay. Sound good? All right. Now, the first column I'm going to indicate are the areas. So the areas, and they're going to be in square inches. So this is pretty simple. So we're going to compute the area of each individual shape. So what's the area of shape 1? 300. And the area of shape 2? All right. And what's the result? Okay, so there's that. If I sum those up, what do I get? 624. Simple stuff, right? Not too bad. Okay. Now, the next one are going to be my Y distances. And what I'll do is this. I will say that those are from the datum. From the datum. Okay. So, let's start off one at a time. Let's start off at shape 1. Okay? Now, what I'm trying to determine is how far it is from the datum to the centroid, to the center of that rectangle, that first rectangle. So I'll walk you through this one. So if I'm at the datum and I want to get to the centroid, which is somewhere about, I don't know, right there, how far is it from the datum to that centroid? 29.5. I go 27 and then half a 5, so 29.5. Did you have a question? Okay. All right. Now shape 2, you tell me, what's that distance going to be? 13.5. Simple, right? Simple stuff. Now, that's A, that's Y. In order to determine the centroid, I'm going to need AY. So I'm going to need to multiply each of those. So tell me what's 300 times 29.5 and 324 times 13.5. We got 8850 and what? Somebody else. There we go. Now, let's go ahead and sum those up. So what do we got? So far, so good? Okay. I can use these quantities to now determine the centroid, the centroid of the whole shape. And I'm going to do that up here up top. I'm going to say that the centroid is the sum of AY over the sum of A, which is 13,224 cubic inches divided by 624 square inches. So y bar equals what? Now, does everybody see where I'm getting at? Just sum of AY over sum of A. So the bottom of those two columns. 21.2, like 21.19, something about like that. All right. So far, so good? Okay. Now, next step we need is we need the moments of inertia of each individual shape. Okay, so I call those I sub zeros or I sub naughts. So I sub naught, inches to the fourth. Okay. Now, what I need are the moments of inertia of each individual shape. Now, let's just go back. What's the moment of inertia of a rectangle? AB cubed over 12, right? So the width times the height cubed over 12, okay? So this top one is going to be the width 60 times the height cubed divided by 12, right? And then the bottom one is going to be the width 12 times 27 cubed over 12. So somebody over here, help me out. $625 for the first one, and for the bottom one. Somebody else. 19,683. All right. Sound good? Any questions? We only need two more things, okay? We need d distances, and then we'll be able to compute the rest of it. Now, the d distances are the distance from the centroid of each individual shape to the centroid of the whole thing, okay? Now, an easy way of computing that is to just take each individual y and subtract the y bar, okay? Now, what you could do is you could actually do the subtraction in the other direction. You could do y bar minus the y. It doesn't really matter because ultimately what we're going to take, what we're going to do with this number, this d value, is we're going to square it. So positive times a positive is positive, and negative times a negative is positive. So it doesn't really matter which direction we do the subtraction in. So help me out. For this first one, we're going to take 29.5 minus 21.1. So what is that going to be? 8 point something. 8.31. And then the bottom one, we're going to take 13.5 and subtract that 21.19, and what do we get? No, we would 7.69. Now, technically it's negative 7.69, but it really doesn't matter because we're going to square it. Sound good? The last thing that we need to do is compute the moment of inertia of each individual shape according to the parallel axis theorem. So the way that we do that is we take the I naught plus AD squared. And so that unit will be in inches to the fourth. So we do that a row at a time. So it's going to be 625 plus 300 times this quantity squared, and then 19,683 plus this value times that quantity squared. Now we'll just take it to one decimal place. So somebody got an answer for the first one? 21,341.8. Is that what you got? Okay, so that number's seconded. What about the next one?
38,843.1.
All right, that number seconded. All right, so add those up and tell me what you get. $60,184.9. Is that number seconded? All right. So I propose then that the moment of inertia is as follows. The moment of inertia is 60,184.9. Okay? That's the moment of inertia. That makes sense? I don't know if you did that in statics or you did that in deformables, but you did it somewhere. So, but if it's been a while, no big deal. It's a pretty straightforward process to follow. It's not really that complicated. And if you've got a really complex cross-section, this is an algorithm that works very well with Excel. So as long as you get your cells locked in right, it works very well. Sound good? Okay. Now, before we move on, I do want to do one more thing. So down here,
Well, a problem like that, what kind of data would they provide us for some of these?
the dimensions, I mean, they'd give you the dimensions.
It's like 3 minutes per problem and 2 minutes per problem approximately. That would make.
Well, first, I don't know if it's 2 minutes per problem or 3 minutes per problem near the end. What's that? Overall, which, that's what I was getting ready to say. Yeah. Yeah, the average is 3 minutes a problem, but or something like that, but that's not as simple because, yeah, some of them you can probably knock out in a few seconds, and some of them are more involved problems. This is probably more on one of the more involved ones on the exam. Sound good? Okay. Now, I do want to refer to one thing real quick. So the centroid of the entire section was somewhere about like right here, wasn't it? And this dimension is, now what was that again? No? Yeah, there we go. 21.19. Now help me out. What is this dimension? Let's see if you can come up with that. What's that dimension going to be? It's not given. You got, well, 10.81. You got to compute that because you know that the entire height of the section is what, 32? So 32 minus that. Okay. The reason why that's important is because when we look at our bending stress profile, our bending stress profile is going to look something like this. Now I'm doing my best to draw this, you know, to scale. Something about like that. So this is going to be the maximum compressive stress that the section is seeing, and this is going to be the maximum tensile stress. So help me out. Do you think this cross-section is going to see, in terms of magnitudes, larger compressive stresses or larger tensile stresses? Tensile, right? Because your bending stress profile is linear and it's farther to the tensile fiber than it is to the compressive fiber. So you're going to get more tensile stresses in the sections. This is definitely a beam that at some point is going to need some rebar. All right. Sound good? Okay. All right. And everybody okay with this? So real quick, in terms of notation, I'm going to call this distance y sub c. Just like last time when we did the rectangular beam, we called this y sub t. Okay? So from the centroid to that extreme outermost fiber, we're calling that y sub t and calling this y sub c. Just so you're aware of the notation that I use later on. I'll give you all a second to copy this down while you're writing.
Doesn't the y sub t really mean like the distance from the centroid to the tensile member?
Yeah, and if I bend this beam, the top's going to be seeing compression. Typically, the bottom's going to be seeing tension.
We're just considering the bottom of the beam to be our tensile.
Yeah, and that's very typical for a beam like this, because think about this. Ultimately, this beam and this this T portion would ultimately be a portion of the floor slab.
Okay.
You see what I mean?
Yeah.
So this is sort of, if you think, one of the ribs of those beams in the parking garage picture that I showed you, remember? So that's going to be those ribs sticking out. They're going to be seeing primarily tension. That flat portion on the top, the slab, it's going to be primarily seeing compression. Does that make sense?
It does. But for the problem before this, ignored those rebar.
Yes.
On the bottom.
Yes.
Because we were only focused on the cracking of the concrete, right?
That's a good question. So in that problem, what we were saying is that the moments that particular beam was seeing were so low that cracking wasn't an issue. Now later on, I mean, you got to understand that moment was something like 25 foot kips. We're going to be talking about hundreds of foot kips later. So the rebar is definitely going to play a role. I mean, it's definitely going to play a role later. Right now, we are talking about lower level moments.
Okay.
Does that make sense?
Yes.
All right. Sound good? Okay. All right. Everybody okay so far? Okay. All right. So for this problem, y sub c is going to be 10.81. Y sub t is going to be 21.19. I'm going to use this to compute the compressive and tensile stresses that we're going to see in the section. Can I go ahead and move on to another panel? All right. Okay. So all right. So now let's go for our cross section. What do we know? We know that the moment of inertia is 184.9 inches to the fourth. We know that y sub c is 10.81 and y sub t is 21.19. Okay. Now what's our moment? Bless you. Yeah, 80 foot kips. So now 80 foot kips, we're going to have a problem with that, right? Not in inches, okay? So let's go ahead and convert that to inches. How do I do that? What's that? Do we multiply by 12 or divide by 12? Multiply. So that's inch kips, okay? And to produce some, I think, usable results in values like PSI, pounds per square inch, I'm going to multiply this to turn it into inch pounds, and I'm going to multiply that by 1,000. There we go. Inch pounds. All right. Everybody okay with that? So if I want to determine the compressive stresses on this section, so I'll say compressive stress, this is basically, if you want, you could think of it as sigma compression. The concrete code tends to refer to stresses with the letter F, so I tend to go along with that. But the compressive stresses are just going to be my over I. So 960,000 inch-pounds times 10.81 inches divided by 60,184.9 inches to the fourth. So what does that come out to be when you compute that? All right, yeah, we'll just keep it to the tenth, so 172.4. PSI? Okay. Now think about it though. That seems like a lot of stress. I mean, 170 PSI. I mean, it's certainly more that are in your tires in your car, right? But in terms of the stresses that concrete can experience, it's actually pretty low. I mean, what are compressive strengths for concrete usually? We're talking about 4,000 PSI, 5,000 PSI. That's only 172. So we're talking about low loadings, okay? Does that make sense? All right. Now that's compressive stress. The tensile stress, or sigma tense, same thing, only we're using that different extreme fiber distance. So while I write this out, you all could probably already have it calculated. All right, so what does that come out to be? 338. There we go. Okay, so that's going to be the answer for part A, because it's just asking for what are the stresses on the top and bottom due to that applied load of 80-foot kips. Not too bad, right? Pretty straightforward stuff. Any questions? Okay, all right. If that's the case, then let's go into this real quick. All right, so okay, so this is part A. If the T-beam is uncracked, calculate the stress in the concrete due to a moment of 80-foot kips. Okay, so that's pretty straightforward. Now let's put our thinking caps on a little bit. So if we have a little bit more data about the section, it's a section that's got a compressive strength of 3,000 PSI. What is the maximum uniformly distributed load that the beam can carry if it's used as a simple span and it's 24 feet long? Okay, so the long and short of it is we're trying to determine what's the maximum load it can carry before it cracks. Now let me be clear, okay? If a beam cracks, it does not mean it's done, okay? Beams can sustain loads far larger than their cracking moments for one very specific reason. We put rebar in the beam, okay? Make sense? So once the tensile regions experience cracking, then the rebar takes over. So this isn't the end, okay? This isn't the end of the beam's capacity. Sound good? Okay. Now, one thing I did sort of glossed over a little bit, and I want to take a little bit of time to discuss. If you notice, I am using some particular symbology associated with this cross-section. For instance, you see this B sub W. That's the width of that lower portion of the cross-section. For you folks in steel design, what do you think the W stands for? The web. Yeah, and for that top part, that B sub F stands for the flange. Okay, so the top part is the flange. This is the web. H sub F is the height of that flange. So that's notation we're going to use later on when we look at T-beams and in more detail. Okay, everybody okay with this? So we're looking at the same cross-section we did before, so we don't have to go through and compute all those properties because we've already got them. Everybody got this? Okay. All right. Oh, pen got all tangled up. Okay, so here we've got a little bit more going on. We've got a section that is simply supported and it's 24 feet long. We're trying to determine how much load it can withstand before it's going to crack. So what do you think the first things we need to compute? What's the first thing we need to do? Or we're trying to, let me ask it like this. We're trying to determine how much load it can be subjected to before it cracks. How do we know when it cracks? When the moment reaches what? The modulus of rupture. So ultimately, we're going to need the cracking moment, right? Everybody okay with that? So we need to determine the cracking moment. And what's the first step in the cracking moment? What What you just said earlier? Modulus of. I'm getting everybody woken up. Come on. Now, to compute the modulus of rupture, what are we going to need? We're going to need FC prime. And what is that? 3,000 psi. What other value are we going to need? What other variable? What quantity? Lambda. And what is lambda? 1. It's in the slides. So right here. Right here. Yeah, it's all listed right there. Oh. So that's 1.0, and that's normal weight. So how do we compute the modulus of rupture? You tell me. There we go, 7.5 times lambda times the square root of FC prime. So tell me what to plug in. 7.5 times 1 times the square root of what? 3,000. Remember, anytime you see that square root of FC prime, you plug in PSI, you get out PSI. So what's that come out to be? What value? We compute that out. Say it again. 410.8. And that's what you got? Okay. 410.8 psi. Now, looking at that value, what can you tell me about the stresses that we computed in the last part? What were the tensile stresses we got in that last part, that last example? It didn't crack, right? Because the tensile stress was something like 338 or something like that. So to actually crack the section, we would need 410.8. So, yeah. All right. Sound good? Okay. Now, what am I going to use the modulus of rupture to compute? What do I need that for? Compute what? The moment that it cracks, the cracking moment. So the cracking moment is computed as follows. We take... Well, you tell me, what's the formula? Waking you all up? Say it again. FR times I divided by YT. Right? Sound good? Remember, just sigma equals my over I, solving for the moment. So we're going to get 410.8 psi times, what's that moment of inertia? 6,000 or 60,000. Was it 184.9? Yes. Divided by YT, which is what? And that comes out to be what? It's going to be a big number, so don't worry. Sure. What are the units? Wait, what? Uh-oh. Uh-oh. You got this. Okay, all right. 1,166,774.7. What are the units? No. There you go. So let's do some conversions to generate a more manageable number. So how would you tell me what to do?
Divide by 12 and then divide by 1,000.
There you go. Did you hear it? Did you hear that? Divide by 12 to get it into foot-pounds and divide it by 1,000 to get it into foot-kips. So why don't I just divide it by 12,000 right now to get it into foot-kips? I'm actually going to write that out. The point is that that's a really quick conversion. So I'm going to say divided by 12,000. So if you divide that by 12,000, what do you get? We'll say to 2 decimal places. 97.23, you said? Is that seconded? All right, so that's foot kips. Does that answer make sense given the data that was in the 3A? Yeah, because 3A had a moment of 80 foot kips. And 80 foot kips wasn't quite enough to cause cracking. We needed a little bit more, and that's a little bit more, so it makes sense. Okay, now, let me ask you this. So the problem is saying if I have a simply supported beam, and the beam is 24 feet long, how much load can the beam carry before it cracks? So let's ask this. So if I have a beam, and you all should definitely know how to answer this since you've all already finished the homework, right? You're already done with it. We have that. We have some load on it. Right? We'll call that WCR, the load that causes cracking, let's just say. And the beam is 24 feet long. Then I'm going to get a moment diagram that looks something about like that, right? That's our moment diagram. So what is this maximum moment right here? WL squared over 8. But if we're trying to determine the load that causes cracking, we're trying to figure out how much load will generate a moment of 97.23 foot kips. So that's how we handle this. We say that our cracking moment is WL squared divided by 8, and we solve for the load. So solving for the load, we would get the cracking load is 8 MCR over L squared. Everybody see how I did that? Multiply the 8 over, divide by the L squared. So that's going to be 8 times 97.23 foot kips divided by 24 feet squared. So what's that going to be? Say it again. 1.35 kips per foot. Now, does that make sense? Everybody okay with that? Now, this is going to sound a little strange, but let me ask it to you in this fashion. So this beam will crack if it is subjected to 1.35 kips per foot. Does that mean that I can literally place 1.35 kips per foot on the beam before it cracks? No. Why? Exactly. There's already load on it. There's a self-weight on it, right? So if you want to determine how much superimposed load would require, it would take to crack the beam, you'd have to subtract out the beam's self-weight. In other words, this beam might by itself weigh 300 pounds per foot, 400 pounds per foot. So you've got to subtract that out in order to determine how much additional load would be required to crack it. Does that make sense? Everybody okay with that? I really wanted that concept to kind of ring true and kind of make sense. Everybody good so far? Any questions? Okay. Now let me sort of start to introduce what's going on with this next example. And we won't finish it, I don't think, but we'll at least get into it. So everybody's okay with this? Okay. So the next thing we have to ask is a question that's been looming on everybody's head is, what happens afterwards? In other words, the cracking moment on that beam was like 97 foot kips. Well, what happens if I put 120 foot kips on it? Well, what that means is that the concrete, or the tensile stresses in the concrete have exceeded the rupture stress, and the concrete in tension is essentially ineffective. Now, that doesn't mean that the beam's going in the river. There is a reason why the beam can still hold up additional load, and that's because we put something in the beam that can handle those additional tensile stresses. And what is that? Rebar. We put some reinforcement in the tensile region. So, hence the principal reinforced concrete design. So I propose that stage 2 behavior of a concrete beam is after it's cracked. So everything that's in tension we assume to be ineffective.
Let's be perfectly clear, when the load is past the moment of cracking, the concrete doesn't do anything. It's not like it still resists up to whatever 97.23 foot kips, but if you put 120 on there, the rebar is not going to withhold like a 3 foot kip. It's going to knock in. Rebar is taking the whole load.
Yes. Okay, now I understand. Yes. The answer to that question is yes, because once the concrete has cracked, it's completely separated. You see what I mean? Once that concrete is cracked, it's separated, and I mean, if I just pull on it, if the only thing that was concrete, it would be gone.
Yeah, but it's not cracked as if parts there.
Well, okay, what I'm getting at is that the concrete has lost the ability to resist those tensile stresses. But the other parts of the beam, they're still gripping onto the rebar, and the rebar is taking over. Does that kind of make sense? Does that make sense? Tell you what, next time I have a video that I can show you that might help clear it up. What ends up happening is when you start loading a beam, okay, what ends up happening is you start to develop these flexure cracks that look something like this. So in this region, let's be clear, the concrete is separated, and let's say at this particular point, the concrete cannot resist any tensile stress. But these regions of the beam are still gripping onto the rebar. I mean, keep in mind, when you see rebar, it's got those ridges on it for a very specific reason. They're taking over resisting those tensile stresses. Now, also, let's also be clear. Beams can resist loads far beyond their cracking moment because of that rebar. Okay? Does that kind of make sense? All right. Everybody else okay with that? Okay. So yeah, so we are basically assuming that the concrete in tension, we're just saying it really isn't doing any good. What is taking over is steel. Now, the problem is this, okay? When you have an element like a reinforced concrete beam, you've got a beam that is comprised of two materials. You know, you've got concrete and you've got steel. The problem is when you break out sigma equals my over I, you are using that formula under the assumption that the beam is made of one material. Okay? The problem is reinforced concrete beams aren't. There's two materials. The way that we assess that is we use what's called the transformed section method. And you probably saw this in 216. I know the folks who took me for 216, we did quite extensively when we talked about composite beams. But the long and short of it is you pick one of the materials and you transform it into the other. So if you remember from 216, you probably did something where you had a composite beam that was made out of like steel and wood, and you might have taken the steel and turned it into an effective lump of wood. So you had a single unified material for the beam. I know you all have seen that before. It might have been a while, but I know you have. Now, the way that you do that is this. So for what we're going to do, we're going to transform our steel into what I'll call an effective lump of concrete. And the way that we do that is we multiply by what's called the modular ratio. So to compute the modular ratio, all we do is this. The modular ratio, we take the modulus of elasticity for the steel, I'm getting ahead of myself, for the steel, and divide it by the modulus of elasticity for the concrete. And I've got that in a couple slides earlier, but I figure I'll go ahead and throw that in here now. So by doing this, and sort of transforming the beam into a single material, in this case concrete. This allows us to go through and use that sigma equals my over I property that was so useful to us before. But we only use that once the beam has experienced cracking. Does this sound reasonable? Do you all remember this from?
The same as stronger over weaker?
Yes, exactly. Did you all do this in 216? I know you did it with me.
Yeah, we did.
Do you all remember? I know you remember it. I was about to say, you all remember it. All right. Let me say this. So that's all I've got for you today. Let me at least sort of give you a preview of things to come. So next time, what we're going to do is look at this beam, and what we're going to have is we're going to have a beam subjected to a moment of 70 foot kips. And what's going to happen is when we go through and calculate the cracking moment, it's going to be less than that. So then we're going to have to break out the transform section method. So hopefully this will address the questions that have been asked. Well, do we ever account for the steel? Absolutely, yes, we do. And this is when it starts. Okay? Is everybody okay with this? All right. You all have a fantastic weekend. We'll see you on Monday. Hey, no class on Wednesday. Okay? I'm not going to be here, so no class on Wednesday, but we'll have class on Monday. Well, yes.